Okay, ladies and gentlemen, so at this time, I'm going to ask that you look back at your Bell responses. I'm going to have you share with the whole class what I call on you. So as we look at our graphical and numerical evaluation of a limit, it's okay to use our graphing calculator technology. It's okay to change our table set, right, to independent variable ask, and put in values of x to get closer and closer to a particular value and see what output values, what y values, what function values are produced in order to evaluate these limits. So now we're using technology, we're doing inspection through graphs or tables, and we're answering these questions. So, in the expression absolute value of quantity x minus 2 closed bars all over x minus 2, as x gets closer and closer to 2, but from the left-hand side, right, what y values are being approached? So what did you get as x is approaching 2 from the left-hand side, what y values are being approached? Preston? 1. So as x approaches 2, but from the left-hand side, -1 is the y value that is being approached. Raise your hand if you get the same as Preston, -1. Keep your hand up if you can answer number 2. Number 2, thanks, hands down. As x approaches 2 from the right, what is the value of the expression approaching? Paul? 1. 1, positive 1. Raise your hand if you get the same. Paul, positive 1? Woohoo! Good, thanks, hands down. And now the overall limit. As x approaches 2, then what's the value of my expression absolute value, x minus 2, all over quantity x minus 2? Brandon? Does not exist. In fact, this doesn't equal anything. And if we had to provide a reason as to why this overall limit does not exist, it would be simple. We would say the left-hand limit does not match the right-hand limit. And so in order for the overall limit as x approaches c to exist, the value of the expression as x approaches c from the left must equal the value of the expression as x approaches c from the right. And here, both of my one-sided limits do exist. It's just that they're not equal to. So the overall limit does not exist. Oh, guys, arm. So an explanation as to why the overall limit doesn't exist. If you were prompted for one, let's say in the future, right, you could say the left-hand limit does not match the right-hand limit. Absolutely. Great. So who does not exist for the third one? Does not exist. Good to go. Great. Let's consider a different expression. As x approaches 3 from the left-hand side, what are the values of this expression doing? And with my visual picture here, our screenshot of the TI-84 emulator, wow, it looks like my function values are decreasing without bound. And so if I'm math man or math woman and I hop on my skateboard here and move along this red function, right, it looks like my y values are decreasing without bound. We can write that, right? We have a symbol for that. So what would we put for that, Anna?
Negative infinity.
Negative infinity, absolutely. And your book talks about how infinity is not a particular value, rather a description of values. Y values are decreasing without bound. And so while this isn't a particular y value, right, we could say that the limit does not exist here because this is not a particular y value. However, by saying that it equals negative infinity describes exactly the manner in which it doesn't exist. We learn a lot by stating this. We can picture what the function is doing as x approaches 3 from the left-hand side. We know the y values are shooting down towards negative infinity. We know there's a vertical asymptote, and we still write this. Okay, we still write this. The limit as x approaches 3 from the right-hand side. What did you get for that, Allie? Infinity positive. So right here, if you had positive infinity for 5, positive infinity for 5, good job. And now the limit as x approaches negative 2. The limit as x approaches negative 2. What are we getting for that? Well, as I'm a man or math woman, and I'm getting closer and closer to negative 2, that looks very smooth and well behaved. So maybe I would go to my my table. Right? Maybe I'd go to my table on my calculator since we're doing these numerically. And wouldn't it be super sweet? We got our Smart View emulator right here as our trusty companion as we go through and evaluate these limits numerically. What if we went in our in our emulator, and we went ahead and entered my expression x plus 2 quantity as a function. So I'll go on my y equals, and I'll go ahead and enter my function, quantity x plus 2, all over, and it looks like quantity x squared minus x minus 6, close. And if I did a zoom 6, I see that we have the exact same screenshot. And as I look at my table, if I had it set to ask, which is my favorite, and I went to my table and I plugged in -2 because it looks smooth and well behaved, I get error, right? I get error. So what's happening with my expression at x equals -2? Why is my calculator producing an error, right? Why am I getting an error there? Meg?
There's a hole.
There's a hole on my graph. There's a hole, which means that my function value is int, right? My function value is int. It's undefined, right? My function is undefined. What in my expression would signal that, right? As you look at your expression, x plus 2 all over x squared minus x minus 6, how could we know that we get an error in our calculator based on that expression? What is it? Where am I getting error in my calculator? What's the error? What's wrong? Sophia?
X plus 2 is a factor in the numerator and denominator.
X plus 2 is a factor in the numerator and denominator, and if I plugged in x equals -2 into my expression and worked it out on paper, what would I get as a fraction? Right? What would I get as a fraction?
0.
Riley?
0 over 0.
0 over 0. And so we've got lots of different ways to tell what's going on here, algebraically, graphically, and in our table, right? Numerically was a goal for last time, that is using graphs and tables and zooms, right? We could go ahead and choose values that are closer and closer to -2 but not equal to, like -2.001, -2.00001, and see what y values are being produced. And so it looks like they're trying to produce the y value here at -2 when I plugged in, I'm sorry, -0.2. Is that what you guys are getting, -0.2? Look at that. So that's closer and closer and closer to -0.2, right? And I can do the same thing from the other side, choosing values like -1.995, -1.999, and see what happens. And so it looks to me like this is trying to tell us -0.2. What's -0.2 as a decimal? What's -0.2 as a decimal? Brandon? -1/5. And so today then we'll algebraically determine if that -1/5 is the actual y value that's being approached. This is in fact a hole because we've got our smooth, well-behaved function. It's undefined, so we have to have an open circle, right? We have to have a hole in our graph here, even though the calculator pixels don't show it because it connects, right? It connects points when it goes to make it in standard mode. We know that there is a hole there because when plugging in -2, I get a 0 on the bottom of the fraction, and that's undefined. However, I get the 0 over 0 fraction, I don't get a constant over 0, and that's going to help in our analytic determination of limits today as well. So there's a big difference between plugging in an x value and getting 0 over 0 versus plugging in an x value and getting a constant over 0, like in the activity, 24 over 0, or -7 over 0, right, or 17.3 over 0. Brandon?
Well, I actually have an objection to the fact that you say the points connect. Rather most of the time calculators skip over those nice and even points. So for example, instead of having an x, instead of measuring at -2, you would have -1.98427, something like that.
Yep.
So it doesn't actually check those points where the errors usually occur.
Absolutely, I'm agreeing with you. In regular connected mode, the calculator's program will take discrete input values of x, plug them in, and then connect them with the pixels that are available to it to create a picture. I could change the mode to not connected, and then it would just plot isolated points, and that could kind of fix your heartbeat problem in the old TI-83s when it made an asymptote line there, and there's no line there, then it doesn't connect the points, and we could change our window so that in the middle, -2, if that shows up right in the middle of the pixels, it'll leave a hole. if we messed around with this and cared enough to take the time to do so.
Or
I'm just saying that the calculator connects points together to make a smooth picture as part of its program. But in any case, we need to be able to verify this algebraically now without the use of a calculator, without the use of our emulator, okay? But first, we want to make sure we're comfortable with a couple techniques. Also know that we'll be having our unit circle quiz as promised. So we've got our unit circle quiz, and we're going to be taking that. It's 12 minutes time. That's the same as the past 3 years students have had 12 minutes. And that's not to be mean. That's because you need to know your values for the unit circle. So every time you're prompted for the value of sine, cosine, or tangent at one of my 16 special points, exact values, we can't start from the ground up and draw your entire circle just so that you can state the value of sine of 2 pi over 3. You have to come up with a mnemonic, a strategy, and memory device so that you're able to reproduce those at will without the use of a calculator and in a timely fashion. So once again, we'll be taking that, and we'll do that non-calculator after closure. We'll have a block of 12 minutes at the end of today's class break, okay? First, let's go ahead and take care of our OTL number 2 check. This time it asks you to take, OTL number 1. Our first one was number 0, the function graph review, self-enroll, signatures, student questionnaire, all that stuff. Now we're at OTL number 1. OTL number 1 came from 2 different sections of your text. At this time in pencil, please give yourself credit for those that you completed out of 18. If you did all of them, then you have 18 out of 18. Divide, enter, multiply by 2. If you got stuck on the spotlight problem where we had the beam of light moving along the wall, and you left that one blank, then you get 17 out of 18. But when you divide, enter, and multiply by 2, you're always going to go and round to the nearest half point. And so by providing stretchers on several of our assignments, we're challenging everybody in your class. We're making some that are a little bit above and beyond what you'd be expected to do, what everyone would be expected to do, but we're not hurting you grade-wise, so long as you're doing almost all the problems. Most likely you'll be rounding your infinite campus score to 2. So we're rounding to the nearest half point, and we're boxing that nice and big. Remember, you're not going to put 1.863. You're going to round that to 2. 1.75 rounds to 2. 1.7 rounds down to 1.5. Everybody go ahead and box your infinite campus score nice and big on the top of your page now in pencil. Brandon?
I'm counting up the problems, and I don't know how you're arriving at
18?
I don't know how you're arriving at 18, because I keep on, I'm counting, oh, you're not counting the A's and B's.
Correct. Yeah, I'm just counting problem numbers, just for simplicity's sake.
Oh.
Very good. Okay, recall, this is based on completion. If you do all your work, you show all your work, you try, get an answer, whether it's right or wrong, you're still going to get a completion score. It's your responsibility to be checking with the hyperlink, or in this case, Unit 1, they're actually just down at the bottom, and Unit 2 for limits. You go ahead and click on the attached resource at the bottom of our Moodle block for Unit 2 limits, and I showed all my work, I even wrote some explanations there with the money and the $10 dividing between friends and stuff like that, and so you can check all of your answers ahead of time, and the burden for that, because of our short class time together in the AP curriculum, is for you to check your answers by yourself. Okay, pass them in straightforward. Please don't left or right pass, just go straight, keep them in the columns. Wait till you receive the people behind you before adding yours to the pile and passing forward. Then you only have to turn around once. Front rowers, if you make sure they're facing the same direction, I really appreciate your help. And I'll get you credit for this in Infinite Campus. Better than paper out. Ah. Thank you. Thank you guys. Thank you. Thank you guys.
We're good. Thank you guys.
Today or tomorrow? Before is probably good for me tomorrow. You can do it? 12 minutes?
Yeah.
That'd be awesome. Otherwise, it's not a big deal. Okay, not tomorrow? Okay. Ladies and gentlemen, thank you for your help passing in your assignment. I appreciate that. At this time, we're going to ask that we switch gears back to our note sheet for today. We're going to be looking, dealing with evaluating limits And graphically, right, graphically we've seen how through inspection we can evaluate many limits whether we have a function rule or not, whether we have an expression or not, whether we can enter a function rule into my y equals many of my calculator. Such is the case with the picture. So I've drawn my blue function f here in our note sheet. Let's go ahead and see if we can answer these. I picked some appropriate c values that we're approaching. Please write down the limit of f of x as x approaches -1 using the proper notation, LIM, the arrow to show approaching. We need to be able to communicate precisely and accurately in the notation using mathematics. Has its language and syntax all its own. So we need to practice writing this. The limit of f of x as x approaches -1. And we saw last class how if the left-hand limit, that is the y value that is being approached as x got closer and closer to -1 from the left-hand side, was equal to the right-hand limit, that is the function value that's being approached as x approaches -1 from the right-hand side, then the overall limit existed. If we have a nice, smooth, well-behaved function, then it doesn't matter if that hole is filled in, that is plugged and has a function value, or is an open circle, undefined, like Meg was talking about earlier. No, the overall limit only cares whether or not the left-hand limit matches the right-hand limit, and because I have no jumps here or breaks, the overall limit at x equals -1 does exist, and it equals the y value, it's like 2. And so I want you to think that, right, we can only talk about limits if we have some sort of open circle, some sort of jump discontinuity, right? We can talk about limits anytime. What I care about is if the left-hand limit matches the right-hand limit, and it need not matter whether the function f is or isn't defined at the x value concerned. Let's go ahead and consider the limit of f of x as x approaches 3, the limit of f of x as x approaches -3, and the limit of x as x approaches 5 from the left. What I'd like for you to do is complete these with your partner right now and check. So I want you, it's okay to talk, I want to make sure you get the same thing.
Oh, I said that's not. That's not. Oh,
Okay, ladies and gentlemen, let's come back together, and I'm going to ask that you share a response with the whole class. So at this time, check with your partner, raise your hand if you got 2, 3, and 4 exact same. 2, 3, and 4 exact same. Thank you, hands down. Marissa Riley, 2, 3, and 4 in that order.
-2 does not exist.
Everybody take a look at Riley and Marissa's answers. -2 does not exist. Infinity, raise your hand if you had all 3. Great, thanks, hands down. -2 is the y value that the function values are approaching as x gets closer and closer to 3 from the left-hand side. Recall the limit, right? The value of the limit does not depend on whether the function is or isn't defined. So if this was an open circle, fine. If we redefine the function to actually take on that y value -2, still fine. It doesn't change the result. If we took that function and moved it down now to equaling -4 for the y value, still doesn't change it. You guys see, I don't care what the function is or isn't at the x value concerned when evaluating limits. Does not exist. How come? The left-hand limit does not match the right-hand limit. And as x approaches 5 from the left-hand side, the function values increase without bounds. So this limit does not exist because this isn't a particular y value. However, by saying that the limit equals infinity describes exactly the manner in which the limit doesn't exist. Okay, that's a descriptor, and that's important because we see a lot about function behavior. Go ahead, 1, 2, 3, 4. Make sure that you're writing limit of g of x as x approaches 0, limit of g of x as x approaches 2, and so on. Check with your partner and see if you agree, and I'm going to have you guys share. Okay, ladies and gentlemen, thanks for your patience. May I have your attention, please? Thank you. Last check with graphical and numerical limit evaluations, right? Graphical evaluation of limits. The limit of g of x is x approaches 0. What did you get for that, Jake?
1.5.
And that was a graphical estimation based on the picture. We didn't have a function rule. We didn't evaluate anything, right? In our calculator, we just do a good inspection, and that looks like about 1.5 or 1.5. So raise your hand if you had 1.5 or 1.5. That's great. The limit of g of x as x approaches 2, right? What did you have for that, Sammy?
2.
Just 2, absolutely. Raise your hand if you had the same as Sammy. Positive 2, doesn't matter if the hole is open or not. The left-hand limit matches the right-hand limit. They're approaching the same y value. Good, so the overall limit exists. The limit of g of x as x approaches negative infinity. What did you have for that? Paige? So negative 2 is the y-coordinate that the function values are approaching as you look to the far left into the graph. And that's end behavior back from pre-calc. Our FST/pre-calc compacted, the end behavior on the left-hand side of the graph, it looks like y equals negative 2 as a horizontal asymptote in this case. Thank you. And lastly, limit of g of x as x approaches negative 1. What did you get for that? What did you get for that limit? Sophia?
0.
0? Raise your hand if you got the same as Sophia. With 0. That's correct. And again, their inspection, the y-coordinates that were being approached as x got closer and closer to negative 1 appear to be 0 from the left-hand and right-hand side. Remember, it could be nice, smooth, well-behaved. There doesn't have to be something going on special, a jump, a discontinuity, an open circle, right? To talk about limits, we just need to consider if the left-hand y values are approaching the right-hand y values as we get close to x equals c, but not equal to. You guys are doing great. Okay, so our limits involving infinity, we already saw. In fact, you've already written this down. Okay, so you don't need to redo this. I just wanted to remind you, because we've run out of time and run short on time in the past, but we had plenty of time last time. So remember that f has a vertical asymptote, right? A vertical asymptote at x equals c if my function values, my y values, shoot off towards positive or negative infinity as x gets closer and closer to a particular x value. And so here we have a vertical asymptote at x equals c if when x approaches c from the right or from the left, my limit goes to positive or negative infinity. My limit doesn't exist when my function values go to positive or negative infinity. F has a horizontal asymptote at y equals L if, as x approaches positive or negative infinity, the value of my limit is the y equals L. So that's when Paige shared the horizontal asymptote when y was approaching negative 2. That's an example of a horizontal asymptote. We already had that down from last time. I just wanted to make sure that you saw it again and we're good. Newsflash. This just in. The TI Smart View emulator is up and running, and I'm super excited about that. What I want to do is show you how you can use your graphing calculator to enter a piecewise defined function. So that's something that you haven't done. At least I don't think that you've done it in the past. So what we're going to do is we're going to take a closer look at our Introduction to Limits practice. And so we need our Introduction to Limits practice. Now try this, the thing you just got to stamp on. Let's look at number 2. So number 2, we had very nice. It's good. I'll grab it right now. Where'd it go? Right here. Maybe if I grab it better. What if I grab it better? All right. So here we go. In our graphing calculator, let's go ahead and see if we can't make this picture. And so here we're going to go ahead and in our graphing calculator, we're going to see if we can make the graph of a piecewise defined function instead of saying, oh, it takes this part, right, this piece of the function here, and then it takes this piece, and so on and so forth. So let's go ahead and in our graphing calculator, enter number 2's p of x, which is given by x plus 1, so long as I'm looking to the left of x equals 2, and is given by 8 over x plus 5 if I'm looking to the right of or equal to 2. So we'll go ahead and in my y equals menu, we'll clear that out, and we're going to go ahead and enter the first piece of that piecewise defined function. And what we're going to do is we're going to divide any term in here. We're going to divide by whatever my restriction is as a quantity. And so I want this rule to apply only when x is to the left of 2. So what we're going to do is we're going to use our test and our logic buttons to determine when that's satisfied. If it's satisfied, then it'll return 1. If it's not satisfied, then it'll return a 0. And by putting this as a fraction, that'll make a 0 on the bottom of a fraction, so it won't produce an output. That doesn't matter at all. We just need to know how to put the syntax. So what we're going to do is we're going to put when x is, and we're going to go ahead and go to the test, which is second math. And we're going to select the less than operator. So the relational symbol less than is the 5th option. Everybody see it? So we're going to go ahead and select the 5th option. Ooh. That's second math is test. X less than 2, close quantity. And so we're going to go ahead and take our regular function definition and then divide the last term by quantity, parentheses, our restriction. X less than 2, close quantity. Brandon?
Are we going to put the first part of the function in parentheses 2?
No.
Like, oh, we're not going to put the x plus 1?
Nope. You can just take any term and divide it by this. I
Oh,
choose to do it to the last one.
I forgot to divide
That's
by
easy to
0.
see.
Anything divided by 0 is an error.
I'm going to go ahead and now put the second piece, 8 over x plus 5. And then I'm going to divide that last term by quantity. You got to do the quantity, x. And now I just want this rule to apply when I'm looking to the right of or equal to 2. So where do we go to get those relational symbols, the greater thans or less thans? Where was that?
Second math.
Second math is test. And this time we want the 4th option, close quantity. 2, close quantity. And so we've told the calculator that I only want this first rule in my y sub 1 equation to apply when x is less than 2, and I only want that second rule, that second picture to be made when x is greater than or equal to 2. I can't wait to try this out. And so we'll go ahead and voila! It appears as though the line, yep, is produced when x is to the left of 2, and it stopped. It's no longer produced if I get equal to 2 or to the right of it, and then here my picture over here is produced when I look to the right of it. That's awesome. And so now we have a means for entering a piecewise defined function. On your first test at the end of Unit 2, one of the questions is a performance question, a performance task. You're going to have to come up and you're going to have to make a piecewise defined function on your calculator and show it to me for points. And so you need to know how to enter this so you can practice doing that. You'll have to be able to enter a piecewise defined function on your own, and you won't be able to ask me how to do it on the test. I'm going to see that you can perform that task on your own. Awesome. That's pretty sweet. Okay, what questions do you have about entering the piecewise defined function? So just dividing a term by, I did the last term by quantity and then your restriction, your domain restriction. All right, let's go ahead and take a look at our objectives for the day. Today we're going to calculate limits algebraically. All right, so algebraically means we're on to our College Board curriculum non-calculator portion of the AP material in the AP exam. So we need to be able to do it non-calculator, pencil and paper only, without the calculator. We're going to determine limits analytically. This is by thinking about expressions using your knowledge of function behavior. And we have a vast library of functions that you guys have been developing over the past 3-4 years, right? You know a lot of functions. You have a library of functions and their behavior, and we can cue in on that when we need to evaluate functions without a calculator by thinking about them analytically in terms of their behavior. And then lastly, we can always verify limits graphically and numerically. If we're allowed to use a calculator, we could always check using our methods from last time. That is, zooming, entering, tracing, changing my table set, etc. let's calculate some limits algebraically if they exist. Remember the bear is there, because sometimes they don't exist, right? But we're going to do our darndest to evaluate them algebraically and analytically. The limit theorems from page 42, that is section 2.3 in your reading, allows us to calculate limits algebraically. We're not going to spend a lot of time. Basically, the sum total of those limit theorems is that if C, my x value of concern, is in the domain of my expression f, then the limit of f of x as x approaches C is simply given by the y value that's returned when I plug in, through direct substitution, C into my function. What? If I'm dealing with a smooth and well-behaved function, where C is in the domain of my function, evaluating the limit is as easy as plug and chug. That is, I can evaluate my limit algebraically through direct substitution, so long as my x value of concern is in the domain of my expression. It's that easy. Let me show you what I mean. Some important basics. The limit of some constant k as x approaches C. Does my expression k, that constant k, depend on x? Will that constant change depending upon what x is? No, and so the y value that's produced by this expression, regardless of what x is approaching, is going to be the constant itself. Graphically, you can think about this as a horizontal line, y equals k. Y equals k is a horizontal line, regardless, as x approaches C, right, over here, my y value returned is still the green y equals k. As x approaches C, when C is over here, the y value returned is the horizontal y value y equals k. What about the limit of x, the identity function, right, y equals x? As x approaches C, what does my expression x approach? Is that a trick? What y value is produced as x approaches C? What does x approach? X approaches C. So the limit of the identity function x as x approaches C is C, whatever C value is being approached. We could also think about that graphically. The number 2, we'll do a blue identity function x. Remember, that's my diagonal line that cuts through the origin at a 45-degree angle. As x approaches C, no matter what C is, it's going to return itself, right? Whatever that is, that's x equals C. What about the limit of x squared minus 3 as x approaches C? Well, it turns out that this graphically, right, this graphically would just be, gosh, that looks like, what library of functions is that? So what is this x squared minus 3 going to look like? Kobe?
Parabola.
A parabola, good. In this particular parabola, whose vertex is typically situated at the origin, y equals 0 when x equals 0 has been shifted, what, down 3 for this one? Down 3 for this one, good. As x approaches C, wherever C is, right, what output, what y value would be produced by this function? Well, whatever is produced by my function rule, replacing my input x with C, and evaluating would give me C squared minus 3. And so if my x value of concern is in the domain of my expression, evaluating a limit algebraically is easy as plug and chug. I plug it in. So we can determine the limit of x squared minus 3 as x approaches 4. Is 4 in the domain of my red function? Most certainly. So I can evaluate this limit simply by plugging in 4 and evaluating. It looks to me like I get 4 squared is 16 minus 3. Is 13. Okay, is 13. So I don't want to make light of the limit theorems, okay? Some teachers and some textbooks make a big deal about the limit theorems and use them to justify each line as they're evaluating limits algebraically. And while we will do some justification and proof in this class, the sum total of the limit theorems is that in the end, at the end of the day, they allow us to evaluate limits algebraically. If my x value of concern is in the domain of my expression, I can evaluate the limit by plugging in through direct substitution, x equals c, and seeing what my rule produces. Let's go ahead then and exit our calculators. So we're going to, our calculators are off and away. They're running off of the screen. We're not going to use our calculators for the initial evaluation. Now we're going to take the calculator away and we're going to switch gears to our algebraic evaluation. Okay? Please find the given limit if it exists, verify graphically or numerically. So here, see it again for the first time. Always, always, always through a direct substitution, we're going to see what we're working with. So as x approaches negative 2, if I were to substitute in negative 2 into my original expression, I would get negative 2 plus 2 is 0 over negative 2 quantity squared is 4 minus a negative 2 is 6 minus 6. So I'm getting 0 over 0. In my activity, last class, 0 over 0. Does this exist? No. Is the function defined when x equals negative 2? No. This would give me an error in my table for my calculator. But my calculator just ran off the screen last slide. I don't have the ability to enter this in my calculator right now and check. So algebraically, I see that 0 over 0, I get an undefined expression. However, this was the 0 over 0, not the 24 over 0. We saw in our graph that this oftentimes did have a value of the limit. While it doesn't have a value of the function at x equals negative 2, the limit did exist, right? And we saw that by adjusting our table set and picking x values that were closer and closer to negative 2, but not equal to. What are we going to do algebraically? Now we're going to do the factoring that you guys, some of you were doing on your activity last time. If initial substitution results in 0 over 0, that's what we call an indeterminate form. So if we produce an indeterminate form, 0 over 0 is our first indeterminate form. That means we can't tell what the value of the limit is or isn't simply by looking at it. So we'll have to try some algebraic manipulations to rewrite that, hopefully in a form where we can evaluate by direct substitution. So we'll go ahead and try some techniques. So what did you guys do in the activity? Several of you last time, what were you doing in your activity to try and evaluate this? Brandon?
I factored both the numerator and the denominator as if they were individual polynomial functions.
Absolutely. So let's go ahead and do that now. We'll go ahead and factor that denominator into a product of binomials. So it looks like x looks like 3 and 2, and looks like minus 3 and plus 2. Is that what you guys are getting? So one strategy for algebraic evaluation of limits is factoring. Factoring won't always work, right? But it's certainly something that we can try algebraically, particularly when we're dealing with a polynomial on top and bottom of an irrational function. Now, because we are evaluating a limit, and we're not concerned what the value of this expression is or isn't at x equals negative 2, we're allowed to cross these out. Now, we can't cross them off, right? Because we feel like it. We can't cross them off because there's an x plus 2 and an x plus 2 on the bottom. We can cross this off because we're evaluating a limit. And so what we're going to do is we're going to write the notation. Where did my plus go? Where did my plus go? We have to write the limit as x approaches negative 2. That's what allows us to cross off the x plus 2's. We can't just write the blue, factorization, because this expression doesn't equal this, right? But the limit of this expression does equal the limit of this, because here's the kicker, ready? When you evaluate a limit, x does not equal negative 2. Because x does not equal negative 2, now I can cross this off. So this is the key step right here. Because we're evaluating a limit, and x doesn't equal negative 2, when we're evaluating the limit as x approaches negative 2, I can cross this out and rewrite as this. You still need the limit notation. You'll lose points on your first test if you drop this limit notation prematurely. You need that limit notation in order to cross out the x plus 2's. In fact, this limit notation has to appear until I'm in a situation where I can evaluate by direct substitution. After I've rewritten as x approaches negative 2, is my c value that x is approaching now in the domain of my rational expression? Yes, it is. And so now I can evaluate through direct substitution. Now is the first time I can not write the limit. Now is the first time I can not write the LIM. This is going to equal 1 over negative 2 minus 3. When you do the direct substitution, that's when you get to drop the limit notation, and now I get the negative 1/5 that Brandon told us in the beginning. of Belwork, and then we saw through inspection with the negative 1.999996. So you already did that before. We've used factoring as a means for evaluating expression. We want to make sure that we're always evaluating our limit, right? We're always doing an initial substitution to see what we're dealing with. We're only going to be searching through our tool bag of algebraic tricks, right, if we generate an indeterminate form. Sometimes we'll be able to determine the value of the limit algebraically without using any of our algebraic manipulation techniques. So here we go. As x approaches 4, is 4 in the domain of my expression? Does 4 cause any problems, like make a 0 on the bottom of a fraction? A negative inside of a square root?
No.
A non-positive input in a logarithm? No. And so I can evaluate this through direct substitution. And the reason I have this example is don't think that, right, that you can't evaluate limits through direct substitution. We always want to try direct substitution before, right, to see what we're dealing with, to see if we have to do any other additional algebraic techniques. So because I'm evaluating this limit and it is in the domain, I can drop my limit right here. Oops. Need 2. As x approaches 4, the value of the expression goes to absolute value 3 minus e, close bars, all over 2. Absolute value negative 5 over 2 is positive 5 halves. Is that what you guys are getting? Awesome. So did we have to do any factoring? Did we have to break up the bars? Right? Meg?
So why don't you write the limit notation before the 5 over 2?
Great question. So why didn't we write the limit notation in here? We could write this limit notation of the original with x's in it right here. That does equal this. We didn't have to write the limit right here because we no longer had x's. This was in the domain of my expression, so I no longer need to write the limit notation. However, I want you to know this limit of quantity as x approaches 4 equals 5 halves. So we could write this. We just wouldn't put the limit right here anymore. We found the value of the limit, and it equals 5 halves. Okay? A good way to think about that is if you still have x's in your expression, you should still have a limit. If you're writing an expression that still has x's in it, you should still have the limit in front of it. You cannot drop the limit until you perform the direct substitution to get a value. Where did we do the direct substitution? First step, and that's why we didn't have to write limit right here. Okay? If you still have x's in your expression, you should have your limit. All right. So let's find the limit if it exists. Darn it! We can't just look along our little graph or calculator for this one with absolute value because we have to do it algebraically. So we're trying to do this algebraically. If I do the right-hand limit, right, the right-hand limit as x approaches 2, then this expression on top, when I do a direct substitution, is approaching 2 minus 2 is 0. Absolute value of 0 is 0. Over, as x approaches 2 from the right, that's values like 2.01, 2.001. The denominator then would be approaching 0 as well, and so I get an indeterminate form. So because I got an indeterminate form, I can't tell because I got an indeterminate form, that just means I can't tell what the value of the limit is or isn't simply by looking at it. So I've got to do some work. I've got to do some algebra. The good news is that we remember how to break up absolute value bars. We know that absolute value, right, is always going to return a positive quantity. How does absolute value return a positive quantity? It considers whether the sign of the quantity inside the bars is positive or negative. If the quantity inside the bars is positive, it'll return the exact same thing. What's the absolute value of positive 13? 13. If the quantity inside the bars is positive, it spits out the same thing. If the quantity inside the bars is negative, then it's going to spit out the opposite thing, right? What's the absolute value of negative 2/3? Positive 2/3. How do I do that? It spit out the opposite of the quantity inside when that quantity inside is negative. So how do we tell? Well, we're going to go ahead and consider the sign that is produced of the quantity inside as x gets closer and closer to 2, but from the right-hand side. Those are values like 2.001, 2.0001, 2.000001. if I'm plugging in values that are closer and closer to but from the right-hand side, then this quantity on top is approaching 0, but it's doing so from which side? The positive or negative side? As x approaches 2 but from the right, like 2.001. Minus 2 is slightly positive, right? Slightly positive. So because I'm approaching 2 from the right-hand side, this 0, right, is being approached, but it's doing so from the right-hand side. That just means that my absolute value bars, because my quantity inside is positive, will return the same or the opposite of what's inside. The same. So when I go to rewrite this with my limit notation, what do I have? What do I have to that I have to be careful of? So when I go to write this with the limit notation, because I still have x's in it, because I'm approaching 2 from the right-hand side, this is going to return the same thing, x minus 2. Over the bottom was always x minus 2. So I've rewritten without bars, and I did it by analyzing the sign of my quantity inside the bars by considering x values that got closer and closer to 2, but from the right-hand side, because that was the one-side limit I was evaluating. Now, because I'm evaluating a limit, and I'm not concerned with what the value is or of the expression is or isn't at x equals 2. Now I can cross that out. This is that over that is 1. And what's the limit of 1 as x approaches anything? The limit of a constant as x approaches 1 from 2 from the right. Is the constant itself, the constant itself. And so in this case, now I'm evaluating the limit, now I drop the limit, and now I get 1. Is that what we got with our picture? Yes, that was our step function. As x approaches 2 from the right-hand side, math woman was on this side of the graph, and we were at positive 1. So we're right. Okay, as x approaches 2 from the left-hand side, those are values like 1.9, 1.99. What's the sign of the quantity inside the bars if x is approaching 1.99? Negative. When I have a negative quantity inside absolute value bars, do the bars return the same quantity or the opposite of that quantity? Opposite, which is what allows me to rewrite this as the limit as x approaches 2 from the left-hand side of absolute value x minus 2 is the opposite of x minus 2 over x minus 2. I rewrote this without bars because x was approaching 2 from the left. The quantity inside bars was negative. I must return the opposite of that quantity. That's the definition of absolute value. Now, because I'm evaluating a limit, I'm not concerned with what the value of the expression is at x equals 2. In fact, x doesn't equal negative 2. I'm sorry, x doesn't equal 2 when I evaluate a limit. I can now cross that out, and I get the limit as x approaches 2 from the left of negative 1, and that equals the constant negative 1. So I've evaluated a left-hand limit, I've evaluated a right-hand limit, and I did it by breaking up absolute value, right, into the quantity itself or the opposite of the quantity, depending upon an analysis of x values approaching from the left or right-hand side. So now, can I do the overall limit? I can certainly say that it doesn't exist. If my left-hand limit doesn't match my right-hand limit, this does not exist. So it does not exist. How come? My limit of my expression f of x as x approaches 2 from the left-hand side does not equal the limit of my expression f of x as x approaches 2 from the right-hand side. So because the left-hand limit does not equal the right-hand limit, then the overall limit does not exist. Okay, let's try another. Let's find a given limit if it exists. So we'll go ahead and do a direct substitution. Everybody, let's plug in 4. I get 16 minus 8 is 8. Minus 8 is 0 over 4 minus 4 is 0. Indeterminate form. If I have an indeterminate form, more often than not, the limit does exist. How do I find it? We'll try some of our techniques. I'm thinking factoring might be a good way to go. Because I have x's in my expression, I need to keep my limit. LIM, you must write this. I'll factor my numerator, I'll factor my denominator. Looks like it already is factored. We'll go ahead and do our factoring. Factoring. I love these. Everyone's like a little puzzle. I'm thinking 4 and 2 and minus and plus. And because we're evaluating a limit, and x doesn't equal 4, then we're allowed to divide out that common factor. You must keep the limit notation while you still have x's in your expression. Or while we're manipulating that. Is 4 in the domain of my rewritten expression? Yes. So how can I evaluate this limit algebraically? Through direct substitution. For the first time, I can drop my limit, and I can let this x go to 4. Which means my final answer is 6. So make the limit of quantity as x approaches 4 equals this. I could write the limit, but I wouldn't put the limit here. I'd put this whole thing there. I would not write limit as x approaches 4 equals 6. This is an operator, just like the sine of theta, right? We don't just write sine. It's a sin to write sine without an input. It's an operator. You don't just write ln, right? You write ln of 4. We write limit of this whole shmam as x approaches 4 equals this. Let's find the limit algebraically. What do we do first? Direct substitution, see what we're working with. What kind of monster are we dealing with here? Well, I get 4 over 4 plus 1 is 5 minus 4 fifths all over 4 minus 4 is 0. So I'm getting 0 over 0. Dun, 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 indeterminate form. I can't tell what the value of this limit is or isn't simply by looking at it. No problem. I've got some tools. Is factoring going to be a good algebraic strategy to try in this case? Oh, I don't see any polynomials, right? Polynomials that produce binomial factors that could cross stuff off. And so factoring does not appear to be a strategy that would be helpful. What else can we do? Call it a day, take an early lunch?
No.
No, we're going to stick with it. I'm subtracting 2 fractions, right, in that numerator. So what do I need in order to combine 2 fractions through addition or subtraction? Right? What do we have to have? Brandon?
We have to have, I forgot what they call it. I know it's a same denominator.
Yes, we need a same denominator. We need a common denominator. So a strategy when combining fractions through addition or subtraction would be a common denominator. So let's go ahead and create a common denominator and see if we can algebraically manipulate this into such a way where the x value concern does exist in the domain of the expression. So here we go, common denominator. So we'll go ahead and rewrite our limit. Everybody, we need to keep our limit as x approaches 4. And we're going to go ahead and rewrite this with a common denominator. And so I'm going to have to take that first fraction, and it looks like I'll need to multiply that first fraction by 5 over 5. To make a common denominator, it looks like I'll have to multiply that second fraction by what to make a common denominator? Quantity x plus 1, so x plus 1 over x plus 1. And that's still all over x minus 4. Haven't done anything with that. All we're doing is trying to make a common denominator for this top 2 fractions so I can combine them through addition or subtraction. Now let's be careful with their signs. Notice how we're keeping the limit expression the entire way through. If there's still x's in my expression, I better keep that limit expression there. That's what's going to allow me to eventually cancel out a factor, I hope, so that I can evaluate through a direct substitution. Here we go, 5x over, and I'll just give it as 5.x minus 1, or x plus 1 rather. I don't need to distribute that through. You may if you want, but I don't need to create more problems. I'll just leave it like that, hoping that something's going to cancel out. On top, 4x plus 1. You want to distribute that through in one fell swoop, or do you want to leave it as 4x plus 1? Alright, we've created a common denominator. Now it's time to go ahead and combine numerator minus numerator. In order to do that, we see that this is going to be 4x plus 4 if I just distribute squiggle underline red. But look at the subtraction. This negative sign applies to everybody in between. So this is going to end up being minus 4x minus 4. Let's write that. Take a minute to make sure everybody sees where that minus 4 came from. Everybody see that? So we've got negative 4 times x plus negative 4 times 1. So we've got a minus 4 there. Everybody good? Everybody good? Good. Let's go ahead and continue on then. How much fun is this? 5x minus 4x is 1x minus 4 over 5x plus 1 all over x minus 4. I have a compound fraction. Ugh. No problem. I know that I can divide fractions by multiplying by the reciprocal. So this is equivalent to, go back down. The limit as x approaches 4 of x minus 4 over 5 times quantity x plus 1 dividing by x minus 4 is the same as multiplying by 1 over x minus 4. Everybody look, that big fraction bar dividing by x minus 4 is the same as multiplying by 1 over x minus 4. And now here's the cool thing. Because we're evaluating a limit and we're not concerned with what the value of the expression is or isn't at x equals 4, we are allowed to divide out the factors and get a 1. So my limit as x approaches 4 of 1 over 5 times quantity x plus 1 will be my algebraic ticket out. Is my x value concern 4 in the domain of my expression? Yes, for the first time. So I can evaluate through direct substitution, and for the first time, I can drop the LIM. I don't have to write anymore right here when I directly substitute in 4 for x. No more x's, I don't have to have my limit anymore. I have to have your limit the whole time here. That's key. That's what's allowing me to do the cross-off. So I get 1 over 5 times 5. Is that what you guys are getting? So I'm getting 1/25. I'm getting 1/25. Hooray! That's way better than 0 on the bottom of a fraction. Right? This is undefined. It doesn't exist. The function does not exist when x equals 4. But we're evaluating a limit. And I'd expect an open circle to be the feature on the graph. Nice smooth well behind, just an open circle. That was 0, 0 instead of 24. Okay, as x approaches 2, direct substitution, go. Check with your partner when you complete. Please provide correct notation throughout. Raise your hand if you already got 3. We got 3. That's good news. Indeterminate form. Let's try some algebra. Factoring look like a candidate for an algebraic strategy that might allow us to rewrite this in a different way. Finally, we get to, because we're evaluating a limit, not concerned with what the value of the expression is or isn't x equals 2, we can divide out the common factors. And then through direct substitution, plug in 2 plus 1 is 3 over 1 is 3. So our final answer is 3. Awesome. All right, as x approaches 2 from the left-hand side, 0 over 4 plus 6 is 10 minus 10 is 0. OMG, I get 0 over 0. So we're going to have to break it up. I'm going to have to evaluate, right, this expression algebraically, and in order to do that, I'll have to determine what those absolute value bars return. Do they return the same thing that's inside or the opposite? Well, it depends. If x is approaching 2 from the left, those are numbers like 1.9, 1.99. If x approaches 2 from the left, but numbers like 1.9, is the sign of this quantity positive or negative? Is there a positive or negative inside there? Brandon?
It's a negative.
Negative. So will my bars return the same thing or the opposite thing?
Yep.
The opposite. That's the key right here, guys. As I approach 2 from the left, the quantity inside the bars is negative, so I have to return the opposite of the quantity inside. Meanwhile, factoring, 5, 2, plus, minus, and because we're evaluating a limit where x doesn't equal 2, I can divide out that divided by that equals negative 1 over x plus 5. All right, we divided out those factors and got 1. Negative 1 over x plus 5 is 2 in the domain of this expression. Yes, for the first time it is, so we can drop the limit for the first time. And you evaluate through direct substitution, I get negative 1 over 2 plus 5 is 7. I'm getting negative 1/7. So I get negative 1/7. I box it, I'm feeling good about myself. All right, we are 1 to go, and then we're closure, and then we're going to circle quiz. Okay, so 1 to go. As promised, we'll have 12 minutes time. And I want to make sure that you see one with a radical. So initial substitution, guys, let's do it. 1 minus negative 3 is root 4 minus 2. Root 4 is 2 minus 2. I'm getting 0 over 0. Initial substitution results in 0 over 0 in indeterminate form. I can't tell what the value of the limit is or isn't simply by looking at the expression, so I've got some work to do. Does factoring look like it'll help? Does finding a common denominator look like it'll help? Are there any absolute value bars to break up? No, and so we have to do a new technique. And so I've opened up, right, my algebraic tool bag, though duct tape and pattern worn it might be, and I'm shuffling around in there and I'm throwing away factoring. Nope, but I'll save it for later. And I'm throwing away absolute value bars, and I need a new one, and that is multiply by the conjugate. And so I'm going to multiply top and bottom by the conjugate. Recall that we ran into that when we were dealing with complex numbers a little bit in advanced algebra a long time ago. The conjugate is the same terms but opposite operation. And so what we're going to do is we're going to rewrite my limit expression, but we're going to multiply the top and bottom by the conjugate of the radical term. So the radical numerator was root 1 minus x minus 2. We're going to multiply the top and bottom by root 1 minus x plus 2. That is the same terms but opposite operation. So same terms, opposite operation. You see how that's root 1 minus x plus 2. Now we'll go ahead and FOIL, right? This is a binomial times a binomial. It just so happens that we've got a radical term, so it's not technically a polynomial. But we'll still do first, outer, inner, last. Let's multiply on top and see what we get. We'll keep my limit expression as x approaches negative 3. Let's do it. First would be root 1 minus x times root 1 minus x is 1 minus x. Outer would be root 1 minus x times positive 2 is plus 2 root 1 minus x. Inner would be negative 2 times root 1 minus x is minus 2 root 1 minus x. And last is negative 2 times positive 2 is minus 4. Everybody check it. First, outer, inner, last. This is all over x plus 3. So what we've done is we've multiplied, right? We've multiplied x minus 3 times root 1 minus x plus 2. I'm going to leave this on bottom. Don't distribute it, because remember, we're trying to create a factor that appears both on top and bottom, so we cross it out. If we multiply this out, we make more radicals and more of a mess. So leave it like this. Why did we choose the conjugate? Notice how these are like terms. In fact, they're exact opposites. So these two terms, without evaluating a limit, right, sum to 0, so they'll drop out nicely. We'll keep our limit as x approaches -3. And we get 1 minus x minus 4 is -3 minus x all over x plus 3 times quantity root 1 minus x closed radical plus 2. I'm sorry, plus 2, yeah, plus 2 the whole time. So we get to what? A roadblock? Can we go any further algebraically? We can. 1 minus 4 is -3. So I get the limit as x approaches -3 of -x minus 3. All over x plus 3. Times root 1 minus x plus radical plus 2. Are we stuck? No. These terms on top share a common factor. In fact, this looks almost the same, except I just have negatives there. No problem. We'll go ahead and factor out a negative. And so we'll go ahead and keep our limit expression. Notice our limit is here the entire time until we do direct substitution. This is negative times x plus 3 over, yay, x plus 3, common factor occurring on top and bottom. I know there's a light at the end of the tunnel. We're close, you guys. We're very close. 1 minus x plus 2, close, and because we're evaluating a limit when x does not equal -3, I can finally divide out that. Once we get your negative, we get the limit as x approaches -3 of -1 over root 1 minus x, close radical plus 2, and now is -3 in the domain of my expression. 1 minus -3 would be 4, and it's okay to have 4 inside of a radical, so absolutely, for the first time, I can drop the limit. I plug it in and work it out, and I get -1 over 1 minus -3 is 4, root 4 is 2, plus 2 is 4. Hooray! Math works. Little worried right around here, right? Little worried, but we stayed strong. We stuck with it. And through algebraic manipulation, we were able to evaluate this algebraic. You guys are awesome. I want to make sure that you're not nervous about this, so we're going to make sure you have plenty of time. Our closure today is brief. What must be true for the limit of f of x as x approaches c to exist? What has to be true for the overall limit to exist? Savannah? So for an overall limit to exist, what has to be true?
Both have to converge.
What have to converge?
The limit from the left-hand side and the limit from the right-hand side.
Yes, the left-hand side must match the right-hand side. So the left-hand limit must match the right-hand limit. Left hand. When initial substitution will result in indeterminate form. 0 to 0 are some tools we can use to rewrite and try again. So it was one thing we did. Hayden? Factoring. Love it. Factoring. What's a different thing we did? Meg?
I'm getting rid of absolute value.
Yeah, break up bars. What was another thing we did? Riley? Multiply by conjugate. This is fun. I'm running out of colors though, so I hope there's just one thing. Multiply by conjugate. What was the last thing that we did with fractions, Lizzie?
Common denominator.
Yeah, make a common denominator. Awesome, you guys are great. Okay, ladies and gentlemen. So our unit circle quiz now is going to be non-calculated 12 minutes time. To do this, we're going to go ahead and take the right-siders. The right-siders are going to slide forward and scoot in front of the left-siders in each part of the to make one long column all the way back. So there's not a partner quiz. So right-sided, you're gonna slide your desk forward, you're gonna scooch over to make one long line. Left-sided, what's that? You can just sit there. You can come and take your name, you might have to shuffle. So right-siders, forward, scooch in. We got 1 minute. Right-siders, forward, and scooch in. Yep, perfect. Yep, it's printed out for you. One long column. Evie, page, yep.
Mr. Chris,